Let the games begin. For as long as I can remember, I've always loved games and puzzles. In fact, it was probably my love of numbers, games, and puzzles that led to me becoming a mathematician. And as I learned more math, I found myself winning more games and solving more puzzles, which made them even more enjoyable. In this course, I will show you that with the simplest of mathematical tools, you can vastly improve your ability to play and understand a tremendous number of games and puzzles. Conversely, we'll see how studying games and puzzles can be a wonderful way to learn some very interesting mathematics. I like the expression, let the games begin, because in most games and puzzles, it's of the utmost importance that you make the right decisions right from the beginning. Let's begin with a game that's fun to play and requires no equipment. You can even play it in the car. I call it the game of 21. Not the card game, we'll talk about that one later. Here's how this one goes. I pick a number between 1 and 3. You then add a number from 1 to 3 to create a new total. I add another number from 1 to 3 to that total. And we continue like this until the total reaches 21. Whoever gets to 21 is the winner. Okay, so for example, suppose I start with 3 and you add 2 to that to get 5. Then I add 3 to that to get 8. You add 1 to that to get 9, and so on. I go to 10, you go to 12, I say 13, you say 16, I say 17, you say 18, and then I win by adding 3 to that to get 21. Now, to make the game fair, you should take turns going first. But if you know the secret, then you'll almost always be able to beat an opponent who does not know the secret. Now, before I give you the solution, play the game a few times to get a feel for it, okay? All right? So what's the secret? After playing a few games, you'll notice that if I ever reach a total of 17, then I'm guaranteed to win, since I am 4 away from 21. So any number that you add to 17, whether you add 1, 2, or 3, I'll be able to add the opposite number, 3, 2, or 1, to reach 21. So by working backwards, the goal of this game is really to get to 17. Now, if we continue that logic, if I can get to 13, which is 4 below 17, I can be assured of reaching 17. And if I can get to 17, I can get to 21. So 13 is my new goal. Well, subtracting 4 from that, if I can get to 9 or 5 or 1, then I can force a win. Got it? So if you get to go first in this game, how should you begin? If you want to guarantee that you can win, no matter how your opponent plays, you should start with a total of 1. Thereafter, you should jump to the totals of 5, which you'll always be able to do, then 9, then 13, then 17, and finally 21. Now, when playing this game against a new player, I usually wait a few turns before jumping to one of my winning numbers. It's not that I'm being nice, I just don't want my opponent to see any pattern too soon. So interestingly, to determine the best way for the game to begin, we had to go all the way to the end. This game illustrates one of our first strategies for successful game and puzzle solving: work backwards from your goal. This strategy is a useful tool for games of pure strategy, but we'll also see in this course how it can be applied to other games of chance. Now here's another game, similar to 21, that if you know the secret, you can literally never lose, although it is possible for the game to be a draw. This one's called the game of 15. Now here, 2 players take turns choosing numbers from 1 to 9. And you're not allowed to repeat numbers. Here, I'll have the numbers 1 through 9 represented by these cards. So we continuously take cards. All right, so players take turns choosing numbers, and the first player to obtain 3 numbers that add to 15 is the winner. That's why we call it the game of 15. If nobody scores 15, then the game is a draw. Okay? Now, since the first player has the advantage, you should alternate who goes first each game. Again, you might want to play this game a few times with your friends just to get the hang of it. All right, so for example, suppose that I start with the number 2 and you pick the number 9. Okay? Then I will pick the number 6. Now notice with 2 and 6, I'm threatening to get 15, so you're going to have to counter that by taking 7, so I can't do that. Now you add up to 16. I'm not worried about you scoring a 15 this time. I'm going to take the number 8. All right? Now, now I'm in a guaranteed win position, because next turn I'm either going to make 15 by going 8, 6, 1, or 8, 2, 5. You won't be able to stop me getting 15 with 2, 8, 5 or 6, 8, 1. Okay? So I won't say that this game is as easy as ABC or as 1, 2, 3, but it is easy as tic-tac-toe. Let's look at all possible ways to create number 15 using 3 different numbers from 1 through 9. Here they are. There are 8 ways to do it, and we can arrange these combinations in a tic-tac-toe board. Look, all 8 combinations appear as lines on a tic-tac-toe board, horizontally, vertically, and diagonally. Mathematicians call this a magic square. So playing the 15 game is really the same as playing tic-tac-toe. And if your opponent doesn't see this, you'll win most of the time and never lose. Thus, in our last game of 15, when I started by choosing the number 2, and you chose the number 9, that was like starting a game of tic-tac-toe where I played an X here, and you played an O there. I could then easily win by picking a 6 in this corner, forcing you to play a 7 here. Thus, if I pick 5 or 8 next, I'm guaranteed to win on my next move. The game of 15 illustrates another useful tip, namely, find a mathematical structure to represent your game or puzzle. You won't always be able to do this, but when you can, it will often provide you with insights that would not otherwise be apparent. Let me say a few more words about tic-tac-toe. Now, most people, here, let's bring up a tic-tac-toe board. Most people know that the first player, X, has the advantage, since if X plays properly, he can never lose, and he can sometimes force a win. As a practical matter, X should start in one of the 4 corners, let's say over here, since O has only one safe response, which is to play in the middle, okay? If O doesn't play in the middle, X can force a win. For example, if O chooses one of these corners, like let's say here, then X can force a win like so. X plays here, O has to play there, X then plays here. Now what can O do? Let's see, O will block by going here, X now wins by playing there. Okay? But now suppose we change the rules so that if someone gets 3 in a row, instead of becoming the winner, they lose instead. Now how does that change the game? It becomes much more interesting, right? This time, since X goes first and has to make 5 of the 9 moves, X is at a disadvantage. But there's a surprise answer. Where would be the worst place for X to start? You would think the worst place would be in the center, right? Because it's involved in the most 3 in a row combinations. And yet, I'll show you that if X plays anywhere other than the center, O can actually force a win. For example, let's say X starts here in the corner, then O should play a knight's move away from him, like say here. Now, if X's next move is in any one of these 6 squares, all right, like one of these 6 squares, then notice that O can just patiently wait until X is forced to create 3 in a row, right? If X was here, then O can just avoid that square, and eventually X is going to have to make 3 in a row. So to avoid that situation, X really has to play here, right? That's the only sensible move. But then O responds here, And now X's only safe move that avoids one of those lines is here, right? Now, but then O can play here, and X doesn't have any safe places to go. For instance, if X plays over here, then O will play here, forcing X to go there, and X now loses with 3 in a row. I'll let you have the fun of figuring out O's other winning strategies, but check this out. If X starts in the middle, he can avoid 3 in a row by always responding to O's move by making the symmetrically opposite play. Like, let's say X starts here in the middle, and if O plays here, then X plays here, right? X will never make 3 in a row unless O makes 3 in a row first, right? If O continues, let's say, by playing over here, then what does X do? X plays there, the symmetrically opposite play, and so on. If O goes here, then X goes here. If O goes here, then X plays here, right? And in this way, X did not lose, even though X had 5 of the 9 symbols. We will find this idea of exploiting symmetry to be very useful in many games and puzzles in this course. As for the strategy of mimicking your opponent, not only does it sometimes lead to a draw, but it can sometimes lead to a win. For example, here's a game that you might say is a cross between checkers and dominoes. It's called Cram. It's played on an 8x8 checkerboard. Here, I'll bring out a checkerboard here, and a bunch of dominoes, okay? The players take turns placing dominoes on the board, and each domino has to occupy 2 adjacent squares. And no square is allowed to have 2 or more dominoes on it. So the game might start this way. You know, you might go here, then I might go there, then you might go here, then I might go there. Okay, and we keep playing until somebody has no legal moves. Whoever makes the last move is the winner. So my question to you is, who has the advantage in the game? Would you rather be first or second in this game of Cram? Now, as it turns out, the second player has the advantage. And by that, I mean the second player can force a win by playing properly. Specifically, the second player can exploit symmetry by always making the symmetrically opposite play of the first player. So for instance, if your first move, say, is here, then I'll make the symmetrically opposite play here. If you then play here, I will play here, and so on. As any time you make a legal move, I'll be able to match it with a symmetrically opposite legal move of my own. Thus, I am guaranteed to make the last legal move of the game. Now, the strategy of copying your opponent's moves is sometimes known as strategy stealing, and it can even be used to prove some interesting results about games. Let's consider the game of hex, invented by the Danish mathematician and poet Piet Hein. It's played with hexagonally shaped pieces on a board that looks like this. There are 2 players who I will call red and blue, who take turns placing pieces of their own color on the board. Red is trying to build a bridge of red hexagons between the red sides of the board, and blue is trying to build a blue bridge between her sides. So for example, in this position, we see that red has won the game because he was able to build a red bridge between the red sides. Now what makes this game interesting is that it can actually never end in a draw. It's impossible. This fact was originally noticed by mathematician and Nobel laureate John Nash. No matter how the pieces are placed, by the time the board is completely covered, there will always be a successful red bridge or a successful blue bridge. Here's an intuitive explanation for this. Think of the 2 blue boundaries as representing a body of water, and the blue pieces as more water. Okay? If a blue bridge is created, then that water will flow from one blue side to the other. If the water doesn't flow, then there had to be a red bridge between them, between the red sides, which prevented the blue water from flowing. So either way, we must either have a blue or a red bridge. I'll leave it up to you to decide if that argument holds water. Anyway, because the game cannot end in a draw, and because having a piece of your color on an occupied space can only be a good thing, it can't get you in trouble to have more territory, then it must be the case that the first player has an advantage. Thus, if the first player uses an optimal strategy, then he's guaranteed to be the winner. Now, what's interesting here is that we can prove that no matter how large that board is, we know that the game is a theoretical win for the first player, even though nobody knows what the perfect strategy is yet. So, how should you begin this game? As you might expect, on this 11 by 11 board, the strongest first move would be in the dead center of the board. But this move is so strong that in most hex matches online and in tournaments, they give the second player a way to make things more even. I'll give the details and say more about fairness in the final lecture. Games and puzzles have an interesting relationship. Sometimes a good puzzle can turn into an interesting game, but sometimes a bad puzzle can lead to an even more interesting game. For instance, consider this 4x4 grid of pegs and beads. Suppose I gave you 32 white beads and 32 black beads to place on the poles in such a way that there's no 4 in a row on any row, column, or diagonal. This is a bad puzzle since it has no solution. On the other hand, that leads to an interesting tic-tac-toe-like game played in 3 dimensions, where you try to get 4 of your colors in a row, column, or diagonal. Since ties are impossible, there's guaranteed to be a winner every time. Another approach to playing games and solving puzzles is through some kind of exhaustive analysis, where you somehow examine every possible position. This works for a small game like tic-tac-toe, but most interesting games have too many possible positions to be handled by this brute force kind of strategy. For instance, the games of Go, chess, and hex have yet to be completely solved even by a computer. There are more legal positions in these games than there are atoms in the universe. In fact, games like Connect 4 and checkers can now be played perfectly by some computers, but they're still enjoyable for most people. Sometimes a solution can be found by applying a smart searching strategy, even without a computer. For example, consider the game of 20 Questions, another great game that needs no equipment. Suppose I gave you a dictionary and I asked you to pick any word from it. I can determine that word by just asking you 20 questions. Many are initially surprised by this, but here's all I'd have to do. If I have a dictionary in front of me, then for my first question, I find the word that's exactly in the middle of the dictionary. Let's say it's the word mathematics. I then ask you if your word is mathematics or earlier in the dictionary. Regardless of your answer, I have cut the number of possible words in half. So if this dictionary has 100,000 words, there are now just 50,000 words remaining. Suppose you say yes, it's below mathematics. Now I'll ask for the word that's in the middle of that list, some word between A and mathematics. Let's say it's the word game, and ask if the word is between A and game inclusive. Your answer will reduce the search space to 25,000 words. So if you say no, then I'll find a word between game and mathematics, let's say Jeopardy, and continue from there. As our table here illustrates, after 17 guesses, we'll have narrowed the possibilities to just one word, and we'd be guaranteed to get it in our 18th guess. Now, how does this apply to the real game of 20 questions? You should typically try to take guesses that have about a 50% chance of getting a yes answer, so the number of possibilities gets cut in half either way. Good questions to start with, say you know it's a person, is male or female, alive or dead, someone you know or don't. The process of constantly cutting your search in half is known as binary search, and if you're allowed n guesses, then you can have as many as 2 to the n possible items and narrow it down to one possibility after your last question. In 1977, Donald Knuth, one of the world's leading mathematical computer scientists, used a smart search strategy to analyze the game of Mastermind. Now, in the standard game of Mastermind, your opponent, the code maker, picks a 4-digit number using only the digits from 1 through 6. So, for example, the code could be 3141 or 6321. Now, in some commercial versions of this game, like here, the code uses 6 colors. But I'll use numbers since they're easier to list and allows you to play the game with just pencil and paper. Your goal is to break the code using just a small number of guesses. For instance, your first guess might be the number 1234. After you guess, the code maker tells you how many of your numbers match the code and how many of those are in the right position. He doesn't tell you which numbers match or which positions are right, just how many, right? Now, in the commercial version, the code maker answers with black and white pegs, or maybe red and white pegs. The black pegs indicate how many matching digits are in the right position. The white pegs indicate how many matching digits are in the wrong position. So, for example, let's do an example here. If the code maker's number was 6241 and your guess was 1234, you would have 3 matching digits, 1, 2, and 4, one of which is in the right position, 2. So you'd score 1 black peg and 2 white pegs. On the other hand, if you guessed 1122, then you'd have 2 matching digits, but none of them are in the right position, so you'd score 2 white pegs. Now here's a math question for you. How many code words are possible? So for our 4-digit number, there are 6 choices for the first number, 6 choices for the second, 6 choices for the third, and 6 choices for the fourth. So the number of possible code words is 6 to the 4th power, 1,296. Your goal is to try to determine the code in a small number of turns based on the responses of the code maker. So what should your strategy be? Now, the answer will depend on your objective. Are you trying to minimize the maximum number of guesses, the worst case scenario? Or are you trying to minimize the average number of guesses? Or maybe you're just trying to find a simple strategy that does well most of the time. If your goal is to minimize the maximum number of guesses, then what Knuth proved was that if you choose your clues properly, you can always get the answer by the 5th guess. Amazing, 1,296 possibilities. You can always figure out the answer by the 5th guess. That is, you would know the answer with certainty after just 4 of your guesses. We call a method for solving a problem an algorithm, and Knuth's algorithm takes 5 guesses in the worst case and about 4.5 guesses on average. If your objective is to minimize the average number of guesses required, then the best algorithm breaks the code in about 4.3 guesses on average, but it occasionally requires 6 guesses. So what's the best opening guess? I always started by picking 4 different numbers, like 1, 2, 3, 4, but that turns out not to be the best opening. What is the best opening depends on your objective. To minimize the worst case scenario, the worst case number of guesses, you should start with 1122, or any two numbers repeated twice, right? So if you wanted to minimize the average number of guesses, then it's best to begin with 3 different numbers, not 4 different numbers, 3 different numbers, like guess 1, 1, 2, 3, or if you were using colors, red, red, blue, green. Now, I've always used a pretty simple algorithm for playing Mastermind. I would start with a random guess, and on each subsequent guess, I would only make guesses that could be a possible solution to the code. I wouldn't try to figure out the best guess, just any guess that would potentially be right. As it happens, this naive strategy performs very well. Although it sometimes takes 6 guesses, it's been shown that this simple strategy takes, on average, about 4.6 guesses, which is almost as good as Knuth's algorithm. Here's another curious property of Knuth's algorithm, is that it's not always the case that the best guess is a potential code word, although that's usually the case. And here's another interesting mathematical result. In 1983, mathematician Vasek Kvatal showed that you could start with these 6 guesses, and no matter what responses the code maker gives, you will always be able to determine the code on the next guess. So this guarantees a solution within 7 guesses. Some games and puzzles are approached using a greedy strategy. For example, when I played the game Monopoly as a kid, I thought the best strategy was to simply buy any property that you landed on. I doubt I was playing the game perfectly, but that seemed like the right way to play. Now, for most interesting games, when you're just getting started, using a greedy strategy is probably not likely to be optimal, but a greedy strategy is better than no strategy at all. As you gain more experience, which is a nice way of saying as you lose to better players, you'll probably switch from using a greedy strategy to something better. In most games, it pays to delay your gratification. For example, we'll see in Lecture 11 on chess that if you focus too early on trying to checkmate your opponent, it can lead to bad results. It's better to try to win slowly and gradually. Try to capture an extra piece or a few pawns first, then simplify the position before going after your opponent's king. Another example comes from that great procrastinating card game known as Solitaire, sometimes referred to as Klondike or Patience. Solitaire is sort of a mix between a game and a puzzle. You have no opponent, and once the cards are dealt, you can think of it as a puzzle of how to eventually bring all of your cards up to the top level. But if you act too impatiently, then you can lose flexibility. It often pays to delay your immediate gratification. For example, in this position, even though we're ready to move the 3 of hearts to the top, that would be premature, since without a 3 of diamonds on the board, we might not have any place to put our black 2s if they show up later among the down cards. There are even mathematical considerations in word games, like say Scrabble or Words with Friends. Many computer programs play these games using a greedy algorithm. Play the word that scores the most points. These programs do tend to play very well against humans, but sometimes playing greedy can be penny-wise but pound foolish. For example, if you have the letter S in your rack, you should not pluralize your word just to earn you an extra point or 2. Instead, you should save that S for a much higher scoring opportunity later. My first tip for a beginning Scrabble player is to only use your blanks and S tiles for very high scoring opportunities. Here's another enjoyable word game that doesn't require any equipment, so it can be played anywhere. And there's enough variety in this game to keep it interesting for a while. In the game of Ghost, 2 players take turns saying letters where the goal is to not create a word that's 3 letters or more. So for example, suppose you start with the letter L, and then I continue with the letter I. You could respond with the letter O, and then the only word, at least the only word that I know of, that starts L-I-O is lion, so I'm going to lose that game. If I tried to weasel out of it by saying another letter like Q, then you could challenge me to give a legal word that starts L-I-O-Q. And since I can't do it, I would lose the round. Now, if you start with L, then a much better response from me would be the letter L, since the only continuing words have the next letter as A. So if I reply with, so it's you say L, I say L, you have to say A, or otherwise I'll challenge you. Then I'll reply with M, and you're going to be forced to lose with llama. So if this game is about words, where does the math come in? Notice that the first player wants to create an even length word, while the second player wants to create an odd length word. To use a mathematical term, we're interested in the parity of the lengths. The first player wants lengths of even parity, the second player wants lengths of odd parity. In this course, we'll see many games and puzzles where parity plays a major role. Now, if you play Ghost and allow any legal word in the Scrabble player's dictionary, then I'm told that the second player can always force a win. But if you only use common words, let's say those that would be recognized by most computer spell checkers, then there's a nice strategy for winning devised by Randall Munroe, who creates the web cartoon XKCD. Depending on your word list, the strategy might change, but all of these words are definitely worth learning. The first player can win by starting with H, J, M, or Z. For example, starting with J, the first player can always force the second player to lose with one of these four-letter words: jazz, jest, jilt, jowl, or just. For example, if I say J and you say A, then I'll continue with Z and you'll be forced to spell jazz. Here are the only words that the first player needs to know to win with the first letters of H, J, M, and Z. Notice all of these words have even length. The way the game is usually played is that when you lose a round, you acquire a letter. First G, then H, then O, then S, then T. Once you've spelled ghost, you're gone. For the cutthroat Ghost player, here are some good words that the second player can usually win with from the other 22 letters. Notice all the words have an odd number of letters. Curiously, the word ghost is one of the winning words for the second player. Maybe that's where the game got its name. Some of the world's best game players have been mathematicians, and we'll meet many of them in this course. Mathematicians have been national and world champions at many games, including chess and checkers, as well as other games like Scrabble, backgammon, bridge, blackjack, and poker. Mathematicians are leading authorities on famous puzzles like Rubik's Cube and Sudoku. One of my favorite mathematicians was Édouard Lucas. He was an expert on the Fibonacci numbers, and he wrote an important book on the mathematics of games and puzzles called Recréations mathématiques. Lucas invented a famous puzzle called the Tower of Hanoi, sometimes called the Lucas Tower, in his honor. The challenge of this puzzle is to move the pieces one at a time from the first peg to one of the other pegs, with the restriction that you're never allowed to put a bigger piece on top of a smaller piece. For example, if your first move is here, then your next move could not be here, because that would place a larger piece on top of a smaller one. So how do you begin to solve this puzzle? And can you do it in the fewest number of moves? Now, the great mathematician George Poya wrote a book called How to Solve It, where he outlined general strategies for solving problems, mathematical and otherwise. My favorite piece of advice was, if there's a problem you can't solve, then there's an easier problem that you can solve. Find it. So instead of n equals 9 pieces, let's solve the 2-piece puzzle. Let's let n equal 2. And that's an easy one to solve, right? We can just go 1 piece here, and then 2, and then 3. So in 3 steps, we've solved this problem. Let's now do a 3-piece puzzle, okay? We'll start here, and suppose I have 3 pieces like that. Now the 3-piece puzzle, we can do this in 7 moves, and it goes like this. We can go 1, 2, 3, like in the 2-piece puzzle, then transfer the big piece over here, that's move number 4, and then in 3 moves I can solve a 2-piece puzzle. 5, 6, and 7. Okay? Let's solve the 4-piece puzzle without going through every little step. Here's the big idea. I know that if I want to get these pieces from here to there, I know that in 7 moves I can solve the 3-piece puzzle and bring them to here. Then in 1 move, I can move the biggest piece over, that's move number 8, and then I can do another 7 moves to get these back to here. So I've solved the problem in 15 moves. For each piece, the number of moves doubles plus 1, right? We went to 1 move, 3 moves, 7, 15 moves, and so on. In general, the problem with n pieces can be solved in 2 to the n minus 1 moves. So the original puzzle, which comes with n equals 9 pieces, can be solved in 2 to the 9th minus 1, 511 moves. According to legend, there exists a giant 64-piece puzzle that's being solved day and night by a priest, and when he solves it, the world will end. If the priest can make 1 move per second, then his solution will take at least 2 to the 64th minus 1 seconds, which is over 500 billion years, so we're safe for now. By the way, if you want to learn how to solve this puzzle quickly, then here's a method that's as easy as 1, 2, 3. Let's call the 3 smallest pieces 1, 2, and 3. And the smallest piece 1 is going to move every other turn, always in the same direction. Okay, so I want you to repeat after me the following mantra. 1, 2, 1, 3, 1, 2, 1, big. Say it. 1, 2, 1, 3, 1, 2, 1, big. Whenever you say a 1, just move the smallest piece to your right. I always use my right hand when I do this, okay? So when you say 2, 3, or big, move that piece with your left hand to whichever space is legal. Okay, now that sounds confusing, but here, let me do it with 5 pieces really fast. Okay, it's going to take 31 moves, so we're going to have to repeat our mantra 4 times. All right, okay. Here we go. 1, 2, 1, 3, 1, 2, 1, big. 1, 2, 1, 3, 1, 2, 1, big. 1, 2, 1, 3, 1, 2, 1, big. 1, 2, 1, 3, 1, 2, 1, big finish. At this point, I should say, as with all of my courses, I'm told that I sometimes go through things pretty quickly. I do that because there's so much good material that I want to share with you. Also, you have control of the remote, so feel free to pause and rewind me as often as you'd like. I don't mind, really. Another way to understand the Tower of Hanoi is by using an object that mathematicians call a graph. Every point on the graph represents a legal position, and those points have a line between them if you can get from one position to another in just one move. For example, with 1 piece, let's look at the 1-piece puzzle. And there are 3 positions, there are 3 pegs, let's call them A, B, and C. So in 1 move, you can go from A to B, you can go from A to C, you could go from B to C, okay, and that's what's represented by that graph. Okay, its graph is just a triangle. With 2 pieces, then there are 9 positions. For example, the point AC, okay, so the first peg is on, the little one is on A and the big one's on C. From here, there are three legal moves you can make. You can either go from AC to BC, you could go from AC to AB, or you could go from AC to CC, okay? So there are 9 positions in this graph. With 3 pieces, there are 27 positions, and the graph looks like this. When you add more and more pieces, the shape of the graph looks like the fractal image known as Sierpinski's triangle. Here's the graph for the 7-piece puzzle. Isn't that awesome? One thing that the graph shows us is that the Tower of Hanoi puzzle is connected in that it's always possible to get from any position to any other position in a legal sequence of moves. As we'll see later in this course, there are many puzzles like the Rubik's Cube and the sliding block puzzle where just because a position is theoretically possible doesn't mean that it's actually achievable from the starting position. But the real reason I show it to you is to give you the idea that there's some beautiful mathematics lurking beneath even the simplest of games and puzzles. As we'll see in this course, mathematicians have been very good for improving our understanding of games. On the other hand, the reverse is also true. Games and puzzles have inspired many a person to study mathematics and have even led to the creation of entirely new branches of mathematics. For example, a puzzle about whether it was possible to walk across every bridge in the town of Königsberg led the great mathematician Leonhard Euler to discover the important mathematical subjects of graph theory and topology. For another example, the subject of probability was essentially born by chance, games of chance, that is. Even though probability and statistics are essential topics for understanding psychology, economics, medicine, and more, they were initially invented to improve people's ability to understand and profit from games. Here's a typical probability problem with a somewhat surprising answer. Suppose you flip a coin 4 times, and you keep track of heads and tails. Now let me ask you, what is the most probable outcome? That all 4 flips are the same? That 3 are the same and 1 is different? Or you get 2 heads and 2 tails? What do you think? Most people expect 2 heads and 2 tails to be the most probable, and yet that's not the case. To see this, notice that there are 16 different possible sequences, all with the same probability. Notice that there are 2 ways to get a 4-0 split, either all heads or all tails. There are 8 ways to get a 3-1 split. 4 of them have 3 heads, and 4 of them have 3 tails. And there are just 6 ways to get a 2-2 split. Hence, there are more ways to get a 3-1 split than a 2-2 split, which comes as a surprise to many. By the way, bridge players use similar reasoning when planning their play of the hand. If you and your partner, say, have 9 spades between you, it's more probable that the other 4 spades have split 3-1 than split 2-2. Games come in all different shapes and sizes, and mathematicians classify them in many different ways. For example, we've seen random games using objects like cards and dice. If a game has no randomness and is just pure strategy, like with chess or checkers, then it's called deterministic. We can also ask, what kind of strategy does your opponent use? Is it predetermined, like in most casino games? Or can your opponent use an intelligent strategy to maximize his chances of defeating you, like in poker or chess? Depending on the presence of randomness and how your opponent plays, we can put most games into one of 4 categories. Most games of pure strategy, like chess, checkers, and Go, are in the first category, deterministic versus an intelligent opponent. Deterministic games against neutral opponents are less common, but we've seen it with the game of Mastermind, and it's probably true of most video games where you're playing against a computer. Most puzzles could be classified as deterministic one-player games. Typically, all of your information is present and there's no randomness. Examples here include the Tower of Hanoi, Rubik's Cube, and Sudoku. Random games against intelligent opponents include games like poker, bridge, Scrabble, and backgammon. Random games against opponents with predetermined strategies include games like roulette, craps, blackjack, and slot machines, including video poker. In fact, we could even classify random games according to where the randomness occurs. In bridge, it happens right at the beginning of the game, when the cards are dealt. After that, it's all about using strategy to infer the missing information. In backgammon, there's no hidden information, right? Players must cope with the randomness of future events, which are dictated by the dice. And in games like Scrabble, blackjack, and poker, you have randomness on both ends. And while we're on the topic of random games, let me say right now that this course does not in any way advocate gambling. On those games where bets are placed, I really just want you to understand the mathematics of the games involved and how to play them. In fact, I'd bet that, all right, bad choice of words. I'm confident that the more you know about the odds and probability, the less likely you are to pursue games of chance, most of which are pretty bad for your bank account. But if you're going to gamble, you may as well at least be smart about it. And besides, many games have real-life applications. We all take calculated risks nearly every day of our lives. In this course, I'll teach you how to do some of those calculations better. Here's a quick preview of what's coming up. The first few lectures will look at specific games of chance, from casino games like roulette, craps, and blackjack, to more complicated games like poker and backgammon. We'll also learn about optimal wagering strategies and the theory of bluffing. After that, we'll look at everything from puzzles you can't solve to games you can't lose, all the way to modern favorites like Rubik's Cube and Sudoku. We'll end with more games of strategy, including an entire lecture on the game of chess. So as we turn our attention to games of chance, like the ones you may find at carnivals or casinos, you may wonder which games are the best and which games are the worst. There's just one way to find out. Do the math and join me for Lecture 2.